Ciao, my name is Muhammad Usman Akbar and I welcome everybody to the presentation of my paper Organ Segmentation with Recursive Data Augmentation for Deep Models. I am thankful to all the co-authors for their commitment and their support. These days, deep learning is an important tool in biomedical imaging as well. The story starts from the extraction of images from a CT or an MRI machine, which are then fed to a neural network for segmentation, and after learning, the model gives us the segmentation masks. The motivation behind the paper was to investigate if the improvement in the input data improves the accuracy of the segmentation task or not. To test our hypothesis, we selected two publicly available datasets. Both datasets were different from one another and have different number of subjects and ground truths available. Chaos has 20 subjects and ground truth available for liver only, while Synapse has 30 subjects and ground truths are available for 13 different classes. We can see the proposed methodology in this paper. We provide an input to the deep model and in return we get the prediction. Once the prediction is received, the input image and the predictions are sent to the data manager where both are concatenated in terms of channel, and then the newly generated data is fed again to the model alongside the original data. If we see in detail, we can see that the first iteration, the input of the model is the training data and we have test data alongside. The training data will produce the prediction, which is then sent to the next iteration via a two-channel converter alongside the original data. The same happens with the third iteration, where the data from the first both iteration is added and then go to the next iteration, depending on where the model stops improving. Here we can again see the proposed methodology in detail. Input image is produce a prediction and that prediction is sent to the data manager where a two-channel generator is working and generates a two-channel image comprising of input data and augmentation mask. Here we can see that each iteration the input data is enriched with newly generated data. For example, D1 is the original data and D2 is the newly generated data from two-channel generated in iteration 1, and this process continues until the improvement of the accuracy stops. For the experimental purpose, we have used the same model for all the experiments, which is FC DenseNet 103. In all the iterations, the model was trained from the scratch and cross-validation was performed for all experiments. Chaos data was distributed into 14 subjects for training. A validation set of 2 subjects and 4 subjects were used for the testing, while Synapse data was distributed into 24 subjects for training, 2 subjects for validation, and 4 subjects for testing. To evaluate the results, we have used the DICE score. The results calculated show that the proposed methodology was helpful in increasing the accuracy of the model for all organs. This is particularly evident for small organs, which are usually more difficult to detect and segment. The DICE score for only 3 iterations are shown for both datasets because first third iterations the results are stable and there is no evident increase in the accuracy after that. It is to be noted that the results shown in both tables are the average DICE scores for the respective test subjects. At the end, we conclude that the proposed methodology was helpful and is not depending on any specific model, and we can actually use any model here, as the enrichment of the training data at each iteration makes the model to diverge in a better way. The proposed methodology was tested on 2 different datasets and results show that there was improvement in the results as well. Thank you everybody. That was all.